Stanford University.
All right, let's begin if there are no other questions. All right. What we're going to talk about tonight is the principle of least action. Now, the principle of least action is a misnomer. Which of the words is wrong? The word that's wrong is least. It is not generally the case that the equations of motion of Newton or anybody else for that matter, classical equations, tell you that the action, whatever that is, we're going to come to it, that the action is minimum. It tells you that the action is stationary. So let's talk about the notion of minimum, stationary, and so forth in, first of all, a simpler context. Let's think about the laws of physics, but a special case of the laws of physics. The special case of the laws of physics is what are the laws determining equilibrium? What are the laws determining the configurations of a system when it doesn't move, when it's not moving, when it's stationary? So that's a question. What are the laws of equilibrium? Equilibrium means that there are no reasons to think the object moves, if it's an object or whatever it is. And the answer, of course, is that the forces are equal to zero. If we have an object and it's not going to move, it doesn't accelerate, let's say it doesn't accelerate, it doesn't move, but in particular it doesn't accelerate, then we can ask what are the laws that govern that? And the answer is that the forces are zero. If the forces are derived from a potential, as all real forces are, if the forces are derived as the derivatives of potentials, potential energy function, which is a function of a collection of coordinates. I'll call them x. Later on tonight I may start calling them q, but for the moment let's just call them x. They could be the coordinates of a particle, they could be the coordinates of many particles. Then the condition that nothing moves is that the forces vanish, which is the same thing as saying that the derivative of the potential. Let's take the case first of all of a particle moving on a line, that the ordinary derivative in that case, the ordinary derivative of the potential, d by dx is equal to 0. That's the condition that the force is equal to 0. And another way of saying that is that that the potential energy is stationary. What does stationary mean? It could mean, it means that the derivative is equal to 0. That's all it means. Okay, but if you want to draw a graph of the potential, where in this graph are the forces equal to 0? They're equal to 0, where the derivative is equal to 0 at the minima and the maxima of the functions. Now, notice, first of all, equilibrium does not require that the potential energy be minimum. It requires that the derivative be 0, which is the right words are that the potential energy is stationary. Stationary means it doesn't change if you move slightly to the left or slightly to the right, and it's just another way of saying the derivative vanishes. But let's think about a small displacement of x. At the moment, we're not necessarily at the minimum. We might be at the minimum, we might be anywheres. And let's think about how much the potential energy changes when we move a little bit. And the answer is, of course, dv by dx times, let's call the motion delta x, times delta x. The change per unit x times a small change in x, and that we can just call delta v. The change in v when we change x a little bit by amount delta x. And what is the rule? The rule is you're in equilibrium when delta v is equal to 0. Now, I made it a little more complicated over here than it was over here. But we're going to find out it's a useful notation, a useful way to think about it, that you're in equilibrium whenever you're at a point where the potential doesn't change when you move a little bit, when you make a little delta of x. Now, of course, this is true to first order in delta x. It's not completely true, but it's true as an approximation for first order in delta x. Now let's go on to a little more complicated situation. Suppose there are several coordinates. I'll draw it as two coordinates because I am not very good at drawing 12 or 15 coordinates. You say, why not 3? Well, the reason not 3 is because I need an axis for v. All right? I only have 2 axes left over, and I'm not even very good at that, but here's 2 axes left over, x and y. I don't know, let's call this x. Let's call this one y. Let's call this one y. All right? And suppose that the potential energy has some shape. It's a function of position, and it's a function which varies both with, now don't get, this is not a roller coaster. This is a hilly terrain which varies in both directions. Then where is an object in equilibrium? Again, it's in equilibrium when all the components of the force are equal to 0, and that means when all of the partial derivatives of v with respect to, let's call it xi now, and xi can mean x or y, or it could mean 59 other coordinates, or 10 to the 23rd more of them. V of x is a function of all the coordinates. Partial of v with respect to any given one of them is the component of force along that particular direction. And when all of them are equal to 0, not one of them, but when all of them are equal to 0, for all I, how do mathematicians write for all I? Upside down A or something. And where do they put the I? Over here? All right, I won't write it right, so I won't even try. dv by dx is equal to 0 for all v. Now, on this side over here, let's imagine, oh, and where is that? Let's first talk about what kind of places satisfy that. First of all, the bottoms of hills are places where dv dx is equal to 0. The tops of hills are also. At the top of a hill, every place you go goes downward. Well, every place you go starts out flat, that's this condition, but then it proceeds to go downward. At the bottom of a hill, you're at the bottom, so any place you go is up, to second order. There are other kinds of stationary points. The other kind of stationary points are called saddle points. A saddle point is, you've all been on saddle points out in the mountains. A saddle point looks like that. Is that clear? I think it's clear. All right, somebody standing over here is in equilibrium. The derivative of v, this is v, with respect to, let's say, y is equal to 0. There's no variation as you go over the top of the hill this way. And it's also 0 if you go this way over here. So you are in equilibrium at this point. But 2 different directions. In one of them, the force, in fact, in one of them, the force pulls you back, and the other, if you deviate a little bit, the other one, the force sends you down the hill. But as long as you're right at the top, you're in equilibrium, right at the saddle point, not at the top, but right at the saddle point. So the generic situation for a stationary point is not that it's a maximum or a minimum, but that it's stationary and there may be different directions where you go down, some directions where you go up, but right at the saddle point, if you move a little bit, the change in the potential energy is 0 to first order. All right. So now what is the change in potential if you move a little bit? Let's say we change x and y, or however many there are. If there were only 2 coordinates, the change in v would be the derivative of v with respect to x. That's the amount that v changes if you move x a little bit, times delta x, plus dv by dy, times delta y. What this says, wherever you are, you don't have to be at the bottom. Wherever you are, the change in v, if you move a little bit, is the derivative of v with respect to x, times the little change in x, plus the derivative of v with respect to y, times the little change in y. And that we can call delta v. It's called delta v. Delta v, a symbol like this means, it's a little bit of an implicit symbol. It means the change in v for any little motion. It doesn't specify which direction or how much you're moving, but for any infinitesimal deviation from the point in question, this is the change in v. And the condition of equilibrium is exactly the same as it was before, that delta V is equal to 0 for every possible choice of delta x and delta y. For every possible choice of the variation. That's the condition of equilibrium. And so we can write then that the general law of nature for equilibrium is that the variation of V is equal to 0 for any little motion at all to first order in small quantities. Okay. That's a sort of summary of all of classical physics when equilibrium is, when there's no time dependence. All right, and it's also, just a little bit of mathematics, stationary points. Now, of course, we're not interested in equilibrium only. We're interested in more complicated motions. We're interested in whole motions. We're interested not in finding points that satisfy the equations of motion, but whole trajectories. Trajectories are curves through space and time. They're functions, x of t, y of t, z of t. And the principle of stationary action is a principle that says not that some point is preferred, but a whole trajectory, a whole function. The problem of finding functions which minimize some quantity is a famous mathematical problem. It's called the calculus of variations, and we're going to go through some examples. We're going to go through a little bit of the mathematics of it. It's not very hard. It's pretty easy. There's an analog of this equation, analog of these equations, just a little more complicated. But let me give you some physical and mathematical examples of questions which are answered by the principles of the variational calculus. For example, the simplest one, which you probably all know, but let's spell it out anyway, is what is the shortest line between 2 points? Shortest means minimum. Minimum means stationary. So what does that mean? You pick 2 points, let's say 2 points on the plane. It could be in 3-dimensional space. It could be whatever you like. But pick 2 points on the plane and ask what curve minimizes the distance between them. The distance now is the incremental distance as you move along the curve. It's not this one, that's for sure. And you all know what it is. It's a straight line. Let's see if we can set that question. If not the answer, let's see if we can set the question up mathematically. So I'll put the origin over here. We have 2 points. Let's call them x. This is x and y 1. This is x2 and y2. And I want to find the curve. Here's the curve, which minimizes the distance between them. That curve is defined by a function. And we could take it to be just let's take this to be the x-axis. Let's take this to be the y-axis. And it's defined by some y of x. Suppose I give you a y of x that passes through these 2 points. Then along that y of x, there's some distance measured along y of x. In other words, you take a tape measure and you hug it to the line. You measure some distance. What is it? Let's see if we can calculate it. If I take some little incremental distance there, let's say it corresponds to dx. There's a little incremental distance dx. Then what's the length of that segment? The length of that segment, of course, the length of that segment, the distance here is dy. The length of the segment is the square root of dx squared plus dy squared. It's the length of this little line here, which is the hypotenuse of a triangle with I don't want to draw too many pieces to this curve here. There's a horizontal distance, a vertical distance, and the length of the little segment, let's call it ds. I don't know what the history is of using s for distance along a curve. I don't know what it is. ds. S is distance along the curve. ds is obviously the square root of dx squared plus dy squared. Let me divide inside the square root by dx squared. All right, then I can take out a dx on the outside, and write this as 1 plus dy by dx squared. Is that much clearer? All I did was divide in the denominator by dx squared, but that means I have to multiply by square root of dx squared, which is just the dx on the outside. That's the distance in this little increment here. And then what's the total distance from here to here? The total distance is the integral, the sum of all these little incremental distances. And so here we are, have it. The distance from 1 to 2 is just equal to the integral of this dx. What do I mean by dy by dx? Y is some function of x. dy by dx is simply the derivative of it. So here's what you're instructed. You're instructed to find the curve that has the property that the integral along it, dx, of the square root of 1 plus the derivative of the function squared, plus the square of the derivative of the function underneath the square root, is equal to the shortest possible length, is minimal. To say that it's minimal means that if you move it a little bit, it'll increase. If you move it this way, it'll increase that, and move it that way, it'll increase. But it also means you're at the bottom of something. You're at the bottom of this quantity with respect to any little change in what the function is. By analogy, with the case of just an ordinary function, we can write that the condition is that the variation of this is equal to 0. The analog of being at the bottom of something is always that the variation, no matter for any little change of what are we going to change, incidentally? We're going to change the function. Any little change in the function will increase the length. Any little change in the function will increase the length in the same way that any motion away from here will increase it. Okay. Implication is that the derivative is equal to 0 or the variation is equal to 0. So the question then is, how do we solve a problem like this? Solving it for us is going to mean one thing. We are not going to frequently be able to solve most problems. This one we can solve. But the answer is a straight line, of course. But solving an equation like this for us is going to mean to reduce it to a differential equation, to an equation similar to Newton's equations. Reducing it to an equation of motion which would allow us to study it in little incremental steps. Right? So solving a variational problem like this means reducing it to a simple differential equation. We'll take that to be a solution of the problem. All right, that's one example. Let me give you some more examples of similar situations. Here's another one, a very similar one. It's the principle not of oh, incidentally, you could ask this question not on the flat blackboard, but you could ask this question on an arbitrary surface. Supposing I give you a surface. It could be the surface of the Earth. It could be the spherical surface of the Earth, or it could be a terrain out in hilly country somewheres. And I would like to put a stake in over here and a stake in over here and find the shortest distance between them. In other words, the shortest route between them. Physically or experimentally, how would I do it? I might attach a string over here, pull the string as tight as possible, and when it's pulled as tight as possible, it will define some shortest distance between them. It will not be a straight line. Why? Because the surface is curved. So you could generalize this question. I won't write the equations for it, but you could generalize the equation here, and it would be the same kind of thing. The distance from here to here would be some integral, sum of little incremental pieces, and the condition that it's minimum or stationary would be that its variation is equal to 0. When you do what? When you change the trajectory a little bit. Not trajectory, but the line a little bit. So that's another example. Principle of, not the principle, but the problem of finding the shortest path between 2 points. The shortest path between 2 points on a curved surface is called a geodesic. And a geodesic on a flat plane is a straight line. Okay, so we all know this. Let's do another one. There is a physical principle, a law, about light. It's Fermat's principle of least time. What's the path of a light ray between 2 points? Okay. Path of a light ray between 2 points. Now, of course, the answer is a straight line. Why is it a straight line? Because the principle is that it should take the least amount of time. That's the principle. The principle of least time, light rays move in a way which minimize the amount of time to go from one point to another. And if the light ray moves with constant velocity, constant speed, then it's just going to be the shortest distance between the 2 points. But you can imagine situations where light moves with a variable velocity from place to place. Like, for example, neutrinos move faster in Italy than they do but no, we don't need to go that route. Light moving through materials moves with a velocity that depends on the index of refraction. Right? Index of refraction can vary from place to place. So supposing we had a light ray moving from here to here with a speed of light which depended on where we were. Right? So here we are, we have a light ray moving from here to here, and the speed of light c is some general function of x and y. It's a function. Then how do we do the problem? Well, let's again construct the time that it takes to go from here to here as an integral. It's clearly the sum of the time that it takes to go every little incremental distance. The little incremental distance, let's go back a step. The little incremental distance from one point to another was the square root of dx squared plus dy squared. Now, that's the distance between these 2 points. How long does it take for light to go between them? Time is equal to distance divided by velocity, right? Time is distance divided by velocity. Here's the distance the light ray goes between here and here, divided by the velocity, but now remember that the velocity is a function of position. We can do the same trick that we did before. Take out the factor dx and write this as 1 plus dy by dx squared. And now our problem is to find the function y of x which minimizes this integral. The thing in the integral depends on both x and y, but also on the derivative of y with respect to x. That's characteristic, that the things in the integrals that we're going to be examining depend not only on x and y, or position, or whatever it happens to be, but also derivatives or slopes of functions. So here's another example, very similar to the, and in fact, this is the way light moves through a medium of variable index of refraction. It finds not the shortest path, but the shortest time that it can go. We don't need to dwell on that very much. I think probably a good many of you know that. But now let's think about mechanics problem. The general mechanics problem, let's take the special mechanics problem first. The special mechanics problem that we always deal with first is a motion on a line, one-dimensional motion on a line. And we can think of the horizontal axis as x, the vertical axis as t. Now, t is the independent variable. Usually you plot the independent variable horizontally, but because time, as everybody knows, flows upward, I got a very interesting, from your granddad, gave me a very interesting paper on the cognitive issue of how time is represented in various cultures. And then how is it represented graphically and in terms of space things? And it turns out that the psychological experiments say that for all people who use an alphabet which proceeds from left to right, they all, here's the experiment they did, a fascinating experiment. They took a bunch of pictures of people, for example, starting with a child, an older child, same person, old man. And they told them to arrange those pictures in a sequence. All people who used systems of writing which proceed from left to right, put them, you know, from left to right, that way. Chinese, who write from top down, put them this way. Child, old man. Israelis, which way they go? The other way. So it's apparent that they envision time differently, this way, for Israelis. And the only people who go from bottom to top are physicists. She didn't say that, the psychologist. I just said it now. It's apparently the only people who realize that time flows upward are physicists. Don't ask me why, I have no idea. But in any case, that's a bit awkward because we also usually think of the independent variable in a graph as the horizontal axis, right? And we like to think of time as the independent variable and position as the dependent variable. What's x of t? All right, so I'm going to turn this graph around. We're going to make this time, this x, and the trajectory of a particle is going to be a curve. Okay? The problem, all right, so there's a standard problem of mechanics. We've talked about it before. If you know the initial conditions, and what do the initial conditions consist of? They consist of knowing the position and the velocity. So on this diagram here, knowing the position is, of course, knowing what x is at a particular time. Knowing the velocity is knowing the derivative. So if you know the position and the derivative at one instant of time, Newton's equations allow you to construct the whole trajectory if you know the forces. You need two pieces of information for each coordinate, a position and a velocity. The other version of classical mechanics is to say, again, you need two pieces of information for each coordinate. Instead of knowing the initial position and velocity, you know the position at time t0, let's call it x0, and you know the position, let's call it, this is at t1, and you know x at time t1, let's call it just x of 1. So what you're given then is the location of an object, a particle, or whatever it is, at two different times, and you're asked to fill in the trajectory in between that corresponds to the actual orbit between those 2 points. Okay. This time, the initial velocity will be part of the solution. You'll need to aim it in the right way with the right velocity to get it to go to that point in space and time. So the initial velocity will not be now an input, it will be part of the solution. Okay. This is the other form of the problems of mechanics, the problems of all of physics. Given an initial and final configuration, find what interpolates between them. And guess what? The answer in all problems of classical physics is to minimize something. Is to minimize something associated with the path between these 2 points. And in fact, that something is an integral from one point to another, and it's called the action. When I say minimize, I mean make stationary. Minimize, maximize, or otherwise make stationary. Something called the action. It's analogous to the distance between 2 points in space, or the time along a trajectory for a light ray. One other example of a problem of calculus of variations, just to make one more example. is the problem of finding the configuration of a chain, a chain with a weight in a gravitational field. All right. Again, it's pinned down at two places. The two places don't have to be at the same elevation. It's pinned down at two places. The chain itself is a function, and you're trying to find a function which minimizes what? The potential energy. The potential energy. Find the configuration of lowest potential energy or stationary potential energy is another one. But all these problems have the character 2 points that are fixed and some integral in between. The potential energy is also an integral. It's the potential energy of each little piece. And some integral needs to be made stationary. Now, what's the connection between this form of mechanics? Well, let's write it out first. Let's write it out first. There is a quantity. Let's call it A for action. It is an integral over the trajectory. So we can write it as an integral dt from T0 to T1 of something that depends on the trajectory. What is that thing? We're going to call it L, the Lagrangian. It's the Lagrangian, and what does it depend on? It depends on, at every point along the trajectory, it depends on the position along the trajectory, and it depends on the velocity along the trajectory, x dot. That's analogous to the situation over here where the thing in the integral depended on both the derivative of the function and the x itself, x, maybe even y. The analogy here would have, well, it would have x being like t. The thing you're integrating over is x. Here, the thing you're integrating over is t. And you're trying to find a trajectory which minimizes a certain quantity. The question is, how do you do that? Or better yet, maybe not better yet, but maybe a little more modest, how do you reconstruct this problem as a problem that looks like Newton's equations? That's what we want to know. What's the connection between this form and Newton's equations? All right, so the first thing I'm going to show you is that such problems can always be reduced to differential equations. So let's see how this works. It can always be reduced to a differential equation, and the differential equation has a name. It's called the Euler-Lagrange equation. Now, the equation depends on what L of x and x dot are. L of x and x dot could be many different things. You could put all kinds of functions in there. Each function that you put in gives you a different Euler-Lagrange equation. But nevertheless, this problem, let's write the problem. The problem is to minimize or otherwise make stationary the action. To make it stationary, in other words, to do the same thing to it as you do when you find the minimum of a potential energy. Make it stationary. Okay, so the way to do it is to reduce it to the problem of minimizing an ordinary function. And the way you do that is by replacing this precise problem by an approximate problem. The approximate problem goes like this. Divide up the time axis into little increments. Replace the trajectory. Replace the trajectory by a sequence of intervals and so forth. Take the size of each increment and call it epsilon. Epsilon, small number. Epsilon is always a small number. Call it epsilon. What we're going to do in the end is shrink it to 0. In the process of shrinking it to 0, we will replace this sort of piecewise straight line by an arbitrary curve. We're going to shrink epsilon to 0. But before we do, let's work out the approximate theory. The approximate theory replaces the integral by a sum. All right, so how do you replace an integral by a sum? integral dx or integral dt. Integral is just a fancy symbol for sum. This becomes summation. The reason the integral is drawn like an S is because it stands for sum. Okay? But we're going to replace that continuous sum, the integral, by an ordinary sum. What are we going to sum over? We're going to sum over each one of these little segments here. Let's call this the ith segment over here. Well, no, let's not use the segments. Let's call this the ith site. This is I minus 1. This is I plus 1. Can everybody read that? I minus 1, I plus 1, and so forth and so on. We'll label these lines I. All right? And let's take into account, first of all, what do we do with dt? What does dt really mean? It means this little distance here. This is what it means. It really means that little distance. That becomes epsilon. dt is replaced by epsilon. Now, how about the action from here to here? Well, up on the top, we wrote that it is an integral of that thing called L over there. So we should write L here. L of, let's see how I did it. I want to get it just the way I did it. Yeah. L of what? L of x sub I. That's the value of x at this point over here. That's replacing x over here. Incidentally, what is x a function of over here? X is a function. It's a function of time. It gets replaced by a function or a discrete function of I. All right, so L is a function of I. And what about the velocity? What are we going to do with the velocity? X dot. X dot is the velocity. What are we going to do with it? Well, we're going to replace x dot by the ratio, the slope basically, the ratio of delta x to delta t. In other words, we're going to replace it by, let's see what it is. Let's write it x sub I plus 1 minus x sub I over epsilon. This is the approximation to the velocity between I and I plus 1. I'm now focusing on the interval between I and I plus 1, right over here. Right. This quantity, this Lagrangian quantity, depends on position and it depends on velocity, and velocity is being approximated by the change in position divided by the time interval. And what do we do with this? We sum it. We sum it over all of these little intervals here. That's an approximation to the action. Now we have a function which is only a function of some discrete variables, x sub I, all the x's. We've replaced the continuous function by a function of these heights. This is an ordinary function now of these heights. And we can ask to make it stationary. How do we make it stationary? By differentiating with respect to the xi's. Let me just in case anybody has gotten confused, I does not stand for the direction of space. It doesn't stand for the particle number. It just it stands for time. Okay. All right, so let's go to a particular point over here, the point I. And let's differentiate this expression with respect to xi. We're changing xi, keeping everything else fixed. Keep everything else fixed, and we're going to calculate the derivative, the partial derivative with respect to xi, moving this up and down, varying it a little bit, of this expression. Now, it varies for two reasons when you change xi a little bit. It varies because xi varies, but it also varies because if you keep xi plus 1 fixed and vary xi, the velocity changes a little bit. So there's two reasons why this expression changes when you change xi a little bit. We have to take them both into account to get the right thing. So let's blow up the region of interest. The region of interest, here's xi over here. Here's xi plus 1 over here. No, this is ti. Sorry, this is ti. No, this is just I. No, sorry. I. Here's xi. Here's xi plus 1. And here's xi minus 1. Xi minus 1. And this is I minus 1. I plus 1. Why don't I bother drawing any more than that? Here's the curve in here. I don't want to draw it flat. Here's the curve in here. The reason I don't need to draw the rest of the curve is because I'm only interested in what happens when I change xi a little bit, keeping all the other ones fixed. So the only terms in this sum which change when I change xi a little bit are these two, the two neighboring intervals. If I change xi plus 1, I have to worry about the next one over. But at the moment, I'm just writing down the change in the action if I vary xi a little bit. I'm differentiating this expression with respect to xi. So let's just focus on these two terms. These two terms are L of xi, I'm rewriting what's there, xi plus 1 minus xi over epsilon plus L of xi minus 1 xi minus xi minus 1 over epsilon. It should all be multiplied by epsilon, but that's not going to make any difference. All multiplied by epsilon. Epsilon is from here. Okay, so I've just selected out these two terms. This one depends on xi over here. This one depends on xi, an interval over. This one depends on the velocity between here and here. This one depends on the velocity between here and here. And I want to differentiate this function with respect to xi. This could be x7. I could be 7, I plus 1, 8, and so forth. Let's differentiate it with respect to xi. Okay. This term depends on xi directly. This one does not. It only depends on xi minus 1. So this one we have to differentiate with respect to xi over here. That will give us epsilon times the derivative of L with respect to xi. And this is xi and xi plus 1 minus xi over epsilon. Let's just call this velocity. Let's just call this velocity I. This symbol I'm just going to call velocity. It's an approximation to the velocity, and I'm going to label it as belonging to the point vi. Now, what about this one over here? This one does not depend on xi. This depends on xi minus 1. So when I differentiate it with respect to xi, I don't get anything. All right. What about when I differentiate with respect to xi from the dependence from here? What do I get? Now, this one's a little bit easier. Let's do this one first. We get plus epsilon L of xi minus 1. Sorry. We're differentiating with respect to xi here. Anybody got to know what to do? Yeah.
Partial L with respect to xi dot, basically. Right?
V.
Or V. Yeah.
Right, good. Partial of L with respect to vi times the change in vi when I change xi a little bit. And what is that? That's 1 over epsilon. The change in vi when I change xi a little bit. Now, what about this one over here? Same kind of thing. 1 over epsilon, derivative of the Lagrangian with respect to the velocity with a minus sign. Why? Because when I move vi a little bit, in this term over here, if let's say I increase vi, then the velocity increases here, but it decreases here. So that means there's a minus sign here. And this is the derivative of L with respect to V, but at point I plus 1. This point is moved forward by 1 unit relative to this one over here. So there are two terms, well, three terms, excuse me. One of them is just the derivative of the Lagrangian with respect to position, and the other two have to do with the derivative of Lagrangian with respect to velocity. But notice that they're shifted with respect to each other a little bit. In fact, this is the difference of two functions at neighboring points divided by epsilon. All times, there's overall epsilon everywhere. That doesn't matter. What is the difference of two functions divided by epsilon in the limit that epsilon is small? It's just the derivative. It's just the derivative. The derivative with respect to what? Time. And so we can replace all of this by simply writing, it's minus, if you keep track of the signs, derivative with respect to time of the derivative of the Lagrangian with respect to the velocity. So it has two terms, the variation, we can write this now, the variation of the action, when I vary xi a little bit, has two terms. It's proportional to d by dt of the derivative of the Lagrangian with respect to the velocity, which is x dot. And there's a minus sign. Let's see. Maybe this one's the minus sign. Plus derivative of the Lagrangian with respect to x. Okay, again, just to go through it briefly again. We just differentiate the Lagrangian with respect to x. That's clearly an obvious thing to do. We want to see how much this thing changes when we vary xi a little bit. That's this term. And then there are two terms coming from the velocity dependence. One associated with the interval in front of that point, and one associated with the interval behind that point. And they come in with opposite sign, because when you move this point up and down, the velocities in the two terms here differ by sign, the change in the velocity. If you move this point up, this velocity increases and this velocity decreases. That's why there's a minus sign, and that's why there's a derivative with respect to time. All right, so the general rule, the action principle, is equivalent. You go to each point, you say the action is really a function of a whole bunch of discrete points. You apply the principle of differentiating and setting equal to 0, and you get you now have an equation at each time. At each time, this equation has to be true. What is the equation? It has to be equal to 0. Differentiating the action with respect to xi and setting equal to 0, that makes the action stationary. This is the general form of Lagrange's equations, the Euler-Lagrange equations. Let's write them down here. If anybody gives you a Lagrangian, you simply spit out the answer. It's a machine. Given a Lagrangian, you spit out, the machine spits out an answer, and the answer is simply a differential equation, d by dt of partial of L with respect to, let's call it x dot, is equal, this one came with a minus sign, this one came with a plus sign, so it's just equal to partial of L with respect to x. That's a general way of, and this is a differential equation. We'll see, we'll work out some examples. This is a differential equation. We'll work out very specific examples.
Question.
Yeah.
So the result that we have, correct me if I'm wrong, it seems like it depends on, that this result is valid for any function of x and x dot. Is that true?
Yes.
You call it a Lagrangian, or it's not a Lagrangian.
You can call it anything you want.
Okay.
You can call it the distance between 2 points. I mean, you can now take, there's an example up there. In that example, x replaces t and y replaces x. I'm sorry I did that, but I did. X replaces t because it's the independent variable, and y replaces x. And you can go through that and apply the Euler-Lagrange equations and get an equation of motion that basically tells you what the trajectory of a straight line is, an equation that has linear solutions, straight line solutions. All right, now, the question. I said that this is an alternative formulation of Newton's equations. What I meant by that is that we can find an L such that when you write down the Euler-Lagrange equations, it is Newton's equation. I will tell you, now we're just going to do it. Now we're just going to do it. We're going to write down what L is for a particle moving in a potential energy. Our potential energy is V of x. Another thing we need is the kinetic energy. This is the potential energy. Let's go P. Kinetic energy, 1/2 m x dot squared. Potential energy and kinetic energy. And now I'll tell you what the Lagrangian is. The Lagrangian, which depends on x dot and x, is just equal to the kinetic energy. And now we could take a vote, but I won't. Should we put in V of x? No, I won't subject you to a vote. The answer is no. You put in minus V of x. Now that's odd, that's weird, right? How come it's not the sum of the kinetic energy plus the potential energy? Well, it's just not the energy. We're looking for something which will have the property that when we apply the Euler-Lagrange equations, we get Newton's equations. The only thing we can do now is to apply the Euler-Lagrange equation and see that it really is Newton's equation. Okay, so what's partial of L with respect to x dot in this formula? Partial of L with respect to x dot is just m x dot, right? In fact, it's the momentum. And that's a good thing to remember, that partial of L with respect to x dot is what we usually call momentum. That's going to recur and recur and recur, and it's going to be our general definition of momentum.
Is there an x double dot in that?
We still have to differentiate with respect to time. So far, I just wrote partial of L with respect to x dot. Now it says differentiate it with respect to time. So this is going to be x double dot. Okay. What about dl by dx? Here's the x dependence. dl by dx is minus, because of this minus sign, is equal to minus dv by dx. Or just ordinary derivative of v with respect to x. dv by dx. Well, if you remember, this is nothing but Newton's equations. One equation. Mass times acceleration is equal to minus dv dx, which we called force. Okay, so at least in this one example, we have reduced the problem of making the action stationary to solving Newton's equations. They're equivalent. Okay? They're completely equivalent. How about many particles and many coordinates? If there are many particles and many coordinates, that means that the x space here is many-dimensional. Things coming out of the blackboard, but the trajectory is still just a curve. The trajectory is now a curve through a many-dimensional space, and we have to apply the same rule to every coordinate, x, y, z, x of particle 1, y of particle 7, and so forth. We have to apply exactly the same rule. First of all, what is the Lagrangian? I should start with what the Lagrangian is. The Lagrangian is exactly the same, except that it's a function of all of the coordinates. I hesitate to write xi because I've used that. I made a mistake. I should not have used I over here. That was a bad thing to do, because by doing it, I use the notation which I'm going to I now stands for the particles and the directions of space. Different I. We're finished with this I. We're finished with that one. We did what we needed with that. We're finished with it. Let's erase that blackboard. I does not stand for discrete time anymore. It stands for X, Y, or Z. It stands for particle number 1, 3, 7, 15. It's all of the coordinates that we're interested in. And Lagrangian becomes a function of all of the coordinates and all of the velocities. All of the coordinates and all of the velocities. And if you go through exactly the same exercise, you can try it out yourself, you go through exactly the same exercise, you find out that at each point of time, at each interval, there's a separate equation for each coordinate. You want to minimize the action with respect to each coordinate. All right? And so all that happens is you have a separate equation for each I. You have a Lagrangian, which depends on all of the coordinates and all the velocities, and the equations, the Euler-Lagrange equations, are simply one equation for each coordinate. All right, so let's go through what the construction is then for many particles. If you have many particles, you do exactly the same thing. Potential energy is V of xi. Kinetic energy is sum over all the i's, mxi, mv squared. Okay? You do exactly the same thing, and what do you get? You get m x sub I double dot, and what happens to dv by dx? It becomes the partial derivative of v with respect to xi. When you vary things with respect to xi, you get things coming from the velocities and things coming from the explicit dependence of v on xi. And what is that? That's just ma is equal to the ith component of force. Now you can see why this had to be minus here. If I would have made it plus, I would have gotten, instead of Newton's equation, I would have gotten mass times acceleration is minus the force. And then I'd have to go back and say, look, I either have to redefine what I mean by force, or I have to redefine what I mean by potential energy. But with the definitions we've used up till now, the Lagrangian is kinetic energy minus potential energy. And that gives you Newton's equations as the Euler-Lagrange equations for the action principle. Now, that's a lot of stuff. That's a lot of stuff, and it's abstract. Is it? Yeah.
So it seems like the Lagrangian and the action principle comes from a kind of working back from the answer. Mm-hmm. Like we want to use calculus of variations, and so we need a functional that's equivalent to Newton's law. Is that the way to look at it?
No.
Oh.
No, it's not the way we will want to look at it. We will want to think about it differently. What we want to think is that the specification of a Lagrangian is an extremely neat packaging of the laws of physics for a particular system. That the Lagrangian, one function of all of the coordinates, which is built out of the kinetic and potential energy, but one function packages all of the laws of physics for that system. So really, I want you to think of it the other way, that the given is the Lagrangian. It's the way physical problems are packaged, and the calculation calculates for you the equations of motion from the Lagrangian. So physicists usually think about the Lagrangian as given, and whenever a new law of physics of some kind is being speculated about, it's never speculated about by writing down the equations of motion. You speculate because it's more convenient, it's simpler, there are fewer unknowns. You speculate about what the form of the action is. So it's one function that packages the entire laws of physics for that particular system. Okay, that's good. That's one reason why it's a useful thing, because it packages things simply. The other reason is because it's an extremely good tool for changing variables, for changing coordinates. We have written down the laws of scones in coffee. In Cartesian coordinates. We could write them down in polar coordinates. We could write them down in your favorite coordinates. We've written them down in coordinates that we've imagined to be standing still. We could try writing them down in coordinates which are moving or accelerating or rotating. We'll do that in a minute. It's complicated to rewrite all of Newton's equations directly in, for example, rotating or other kinds of coordinates. It is a lot easier to rewrite the Lagrangian or the action in an arbitrary coordinate system, and then once you have the Lagrangian, you can construct the equations of motion. The point is that the action principle is really a statement that doesn't depend on the coordinates you use. If I tell you that the shortest distance between here and here is a straight line, that doesn't depend on what coordinates I use on the table here. I could use Cartesian coordinates, I could use polar coordinates, I could use curvilinear coordinates of all kinds. The physical fact that it's a straight line is independent of the coordinates. And the physical fact that the straight line is the shortest distance between the 2 points does not depend on the coordinates. So when I say a straight line is the shortest distance between 2 points, that's true in any coordinate system. The action principle in the same way is true in any coordinate system. If you change coordinates, the form of the equations of motion change, but the actual value of the Lagrangian doesn't. So we're going to do some examples of that type. I don't know, maybe we're up to that now. All right. So it's an extremely convenient tool for changing coordinates. Let me give you the first example. The first example is taking a simple particle, and this is a terribly complicated problem, in fact. If you try to do it directly, taking Newton's equations, or even just forget Newton's equations, just the equation for without any force, just forget forces, just the equation for a particle moving in a straight line. And what I'm interested in now is two frames of reference. One is a stationary frame of reference, an inertial frame of reference, and in this frame of reference, Newton's equations apply. And in fact, we're going to set force equal to 0, so that just says mass times acceleration equals 0, mass times y double dot is equal to 0. It's a two-dimensional problem. The other coordinate system, which I'll draw in red, looks like this. Now that's pretty easy, except we're going to make it harder. We're going to make it harder by making the red coordinates rotate with time. All right? And ask, in other words, it's physics as seen by somebody standing on a carousel. What do the laws of physics look like? In particular, the simplest of all laws of physics, what does it look like and how do we describe it from the viewpoint of a turntable or a carousel? You might have a little bit of fun trying to work it out directly without ever having heard of the Lagrangian, and then try it with Lagrangian, and I think you'll find that the Lagrangian is the fast way to do it. Okay. The blue coordinate system is described by little x and little y. The red coordinate system is described by big X and big Y. Can I prove that? No. You're supposed to laugh at that. Okay. The angle between the x-axes is theta, but theta depends on time. In particular, theta is going to depend on time like omega t. In other words, it's a uniformly rotating coordinate system. You can set omega t equal to theta if you want temporarily. And now the question is, what is the coordinate transformation between the big coordinates and the little coordinates? I'll let you work that out. I'm going to give you the answer. The answer is little x. I'm going to write little x and little y in terms of big X and big Y. Little x is equal to big X times cosine of the cosine of the angle, cosine omega t, plus big Y times sine omega t. How about little y? Anybody want to take a shot at it? Minus x cosine, sine omega t. Plus y cosine of omega t. That's correct. You can check this. You have to sit down and do a little bit of coordinate change. This doesn't depend on the fact that the coordinate system is rotating. If you just call omega t theta, you'll see that this, and experiment around with it, you'll find out that this is the way two-dimensional coordinates change if you rotate by angle theta. All right, now here's what we know. We know in the little coordinate system, let's give them names. Let's not. In the stationary coordinate system, the non-rotating coordinate system, Newton's equations and Newton's laws are the right laws, and we can summarize that by writing a Lagrangian. The Lagrangian in action. Integral L dt with L equaling little 1/2 m over 2 x dot squared, little x dot squared plus y dot squared. No potential energy, the simplest thing with no potential energy at all. If we apply the Euler-Lagrange equations to this, we'll just get mx double dot is equal to 0 from the left-hand side. Mx double dot is equal to 0. No potential energy, so there's no right-hand side at all. Same thing for y, and that just tells us that things move without acceleration. How do we work it out in the big coordinates? Well, we say all we have to do, the principle is the same. The principle is the principle of least action, but all we have to do is rewrite the action, or the Lagrangian, in terms of big X's and big Y's. That's not hard. It looks much harder than it is, but it's easy to do. All we have to do is figure out what x dot and y dot are and plug them into here. So I'll write down the answers for you. You can check them. Little x dot is equal, we're just going to differentiate this with respect to time. It's big X dot times cosine omega t. Oh, it's going to take more room. All right, let's do it. Cosine omega t, and now we have to differentiate the sine. Sine also depends on time. So what's the derivative of this term? Am I making a mistake? Oh, sorry. We're doing this one. Yeah. Yep, we need a factor of omega, omega x, times the derivative of the cosine, which is sine omega t. I think I have the sine. Here's the sine, right? Good. Now we have to differentiate this. Oh, it's plus y dot sine omega t, and then plus omega y cosine omega t. Straightforward differentiation of x with respect to t. You do the same with y. You do the same with y, and then you calculate x dot squared plus y dot squared. It looks a bit messy, but it's really very simple. It takes just a little, essentially by inspection. And I will tell you what it is. We're rewriting the Lagrangian in terms of the big coordinates. You have to use over and over again cosine squared plus sine squared is 1. For example, well, let's just see what's in y here. There's going to be another term in y dot. I'm not going to write it all down. I'm just going to write one term. Y dot is going to have minus x dot sine omega t, right? Plus all sorts of other stuff. What happens when I square this one? Sorry, when I square this x dot squared plus y dot squared, little x dot squared plus y dot squared, I'm going to get big X dot squared cosine squared and big X dot squared sine squared. That adds to 1. So I can be pretty sure there's going to be an m over 2 times big X dot squared. Likewise, when I square y, where's y dot? When I square y dot squared, I'll also get a big y dot squared. And both of these will multiply sine squared plus cosine squared, which is 1. Now, the next type of term which appears will be what happens when I square this term over here. This is going to have an omega squared, an x squared, and a sine squared omega t. I will also find in here an omega squared, x squared, cosine squared omega t. Just spend a few minutes with it. So what I'm going to find is, I think it's plus omega squared. What you get is dot, well, let's see, this x dot by this y over here. Cross terms with x dots and y's, and y dots and x's. The last term that you get, and that only has 1 power of omega in it. So that's, I think, plus or minus. Let me just see what the sign is. Plus omega times x dot y minus y dot x. All the variables on the side are the rotating coordinates. That's what you get. As I said, it looks much harder than it is. I don't want to go through the algebra because I make algebra mistakes all over the place, but this is what you get. No sines and cosines left over. They all come in the pattern, sums of squares, or they just cancel. Okay, so this is what you get. Now, what do you do with it? You say, principle of least action. We think of this as the Lagrangian. The rule is principle of least action, and so we apply the Euler-Lagrange equations to it. Let's work out the Euler-Lagrange equation for x. I think I can, well, let's put this up. Put this up, pull this down.
Just the P of the other parentheses are a bracket outside.
Yeah, yeah. There's an m over 2 multiplying this, and there's an m over 2 multiplying this, and there's a plus sign. Yeah, from the m over 2, that's exactly right. Okay.
Also, aren't those Y's capital Y's?
Yeah, they are. Everything is capital on the side. Sorry, I see. Before we do the Euler-Lagrange equations, let's just look at this for a minute. First of all, if omega is 0, if the coordinates are not rotating at all, omega equals 0. This just looks like the good old Lagrangian for x and y. And what are we going to get? We're going to get that things move in straight lines in the capital XY coordinates. Of course they are, if the coordinate system is not rotating. Now let's forget for a moment this term over here and look at this term. This has the look of a potential energy. It's a function of x and y. Remember what we normally would write. We would normally write that the Lagrangian is equal to t minus v. So this has the look of a potential energy where the potential energy here, it's a fictitious, but you can call it fictitious if you want, call it a fictitious potential energy. A fictitious potential energy, V fictitious, which is equal to minus omega squared m over 2 x squared plus y squared. Capital X squared and y squared. Minus because the Lagrangian always has t minus v. What would a potential energy like this do to a particle in xy space?
Like a radius there, it looks like a radius.
It's a force.
It's a potential energy which depends on the square of the distance from the origin. Which way is the force pointing?
It's outward, right?
Outward, radially outward. You have a potential energy which falls off in any direction. X squared plus y squared is r squared. The potential energy is negative. That means you're on the top of a hill at the origin. If you're at the origin, you're at the top of a hill, and the top of the hill is falling off quadratically. What is this? It's the centrifugal force. If you're on a rotating carousel and you put a particle down on the floor, it'll get pushed out toward the edge by centrifugal force. So this is just centrifugal force. This one is Coriolis force. Okay, it's Coriolis force. And notice it's a new kind of term in the Lagrangian. It's a new kind of term which depends both on coordinates and velocities. Linear in velocities and coordinates. It's something new. It leads to a kind of force. Whenever you have a situation like this, it leads to a kind of force which is called a velocity-dependent force. So to see how it works, what we want to do is write out the Euler-Lagrange equations. Let's write out the Euler-Lagrange equation for x. We start with partial of L with respect to x dot. What is that? mx dot what we usually call momentum, but now there's another term. It's m omega over 2 times y, derivative of L with respect to x dot. So let's add that in, plus m omega over 2 times y, right? Did I get that right? Now, what are we supposed to do with this? We're supposed to take d by dt of it. What does that give us? mx double dot plus y dot. And what does that equal? It equals the derivative of the Lagrangian with respect to x. Does it depend on x? Yeah, you bet it depends on x over here. So there's an omega squared m times x. And it depends on x over here. That's minus m omega over 2 times y dot. Plus or minus? Oh, sorry, wait. We're supposed to set this equal to this, right? Yeah. Partial of L with respect to x dot equals partial of L with respect to x, equals. And what's the other term? The other term should be plus m omega over 2 y dot. Comes from here. Differentiating with respect to x gives us m omega over 2 times y dot. Now the sign, do I have a sign mistake? Yes, I have a sign mistake over here, coming from this sign over here. Okay. Now this doesn't look too familiar, but I can make it look more familiar by saying, look, this is what I call acceleration, and this is ma. Let's put everything on the other side. Let's put everything on the other side and call it the fictitious force. What does a fictitious force have? It has omega squared m times x. What is that? This is the x component of acceleration. It's a centrifugal force. It's a centrifugal force. Centrifugal force, the component of it is proportional to x. The x component of it is proportional to x. What about the other term? The other term, they add minus m omega y dot. And now we have something truly new. We have a force on the right-hand side which is proportional, it's the x component of force, which is proportional to the y component of velocity, or minus the y component of velocity. Okay. It's a velocity-dependent force. It's called Coriolis force. I'm not going to go into why hurricanes work and to show you how the details are. Just what I'm mainly interested in is showing you how the action principle makes calculations like this easy and fast. Right? What about the y component of equation? It's m a sub y, or m a y, y double dot, is equal to omega squared m times y. This is capital Y, and then plus m omega x dot. Okay, so there's an effective force seen on the rotating turntable or on the carousel, which is centrifugal force. It looks sort of like a garden variety potential energy. Except it's pushing outward. And then a velocity-dependent force, a new thing, a new kind of thing. We might not have guessed it very easily. Well, we might have or we might not have, but it's packaged extremely neatly in the action principle.
Would this work for arbitrarily curved coordinates?
Yes,
as well?
yes, for any coordinates. And not only can the coordinates be curved, but they can be time-dependent. Here, these coordinates were not only curved, but they were also time-dependent. Let's do another simple example. This is an even simpler example. Polar coordinates, just ordinary polar coordinates, not time-dependent, not moving, ordinary polar coordinates. And work out the equations of motion for an ordinary particle with a potential which depends on radius, let's say. Okay, so what's our coordinates? Now our coordinates are just, this is x and this is y, this is r, and this is theta. Okay. I want to write down the 1/2 m x dot squared plus y dot squared. But I want to write it in terms of r and theta. Okay, that's easy. You just write that x, now theta is not changing with time. And either theta is now the theta coordinate of the particle. It is changing with time. If the particle moves, theta changes with time. Okay? And so does r. All right. But x is equal to r cosine theta, y is equal to r sine theta. We can take the time derivative of x, the time derivative of y, square them, and add them together. What do we get? This is equal, I'll tell you what it is. It's 1/2 m times r dot squared. That's the term coming from r. And then there's a term coming from theta, and it happens to be plus r squared theta dot squared. Now, as I said, you get this simply by differentiating x with respect to time. X dot, for example, will be r dot cosine theta plus r minus r sine theta theta dot. Y dot will be r dot sine theta plus r cosine theta theta dot. Let's look at it. X dot squared plus y dot squared. X dot squared will have r dot squared times cosine theta plus cosine squared plus sine squared. So that'll be your r dot squared. It'll also have r squared sine squared, cosine squared, and theta dot squared. That's this term here. And what about the cross terms? You'll have this times this, and they cancel. So this is then the Lagrangian in polar coordinates. If I want to add a potential energy, let's add a potential energy. That will be minus V of r. I'm taking the case now where the potential energy depends on distance from the origin. It could depend on theta too, but for our purposes now, it's called the central force problem. The central force problem, the potential energy only depends on distance from the origin. And there it is. Now we can write down the Euler-Lagrange equations very simply. Okay, the Euler-Lagrange equations are now for r and theta. R and theta are our new variables. So what is the Euler-Lagrange equation for r? You start with partial of L with respect to r dot. R is replacing one of the x's. And that's, sorry, there's an m here, isn't there? That's mr dot. And that's it, right? That's partial of L with respect to r dot. We have to differentiate this with respect to time. That gives us mr double dot. What is that? That's the radial acceleration. And it is equal to the sum of two terms. The first term is the derivative of Lagrangian with respect to r contains, looks like it's equal to m r theta dot squared. And then from here, minus dv by dr, derivative of v with respect to r. What do we have here? First of all, you might have guessed this in the first place. This is the r component of force. R component of acceleration, r component of force. What is this thing over here? It's again a centrifugal force. It's a centrifugal force not because the coordinates are rotating, but because the particle itself may be changing theta. As the particle changes, as particle is moving around, whipping around, it also experiences a force outward proportional to theta dot squared. So that's the r equation. What about the theta equation? The theta, this is of course, tells you how r changes with time, but you have to know what theta dot, you have to know what theta is doing. So the question then is, what is theta doing? To find what theta is doing, you work out the Lagrange equations for theta. All right, so that's d by dt of partial of L with respect to theta dot. That's the left-hand side. And what does that give? That gives m r squared theta dot, right? d by dt of m r squared theta dot. And what's it equal to? dl by d theta. That's the other part of the Euler-Lagrange equation. The other half of the Euler-Lagrange equation is dl by d coordinate. Well, what is dl by d theta? L doesn't depend on theta. It depends on theta dot, but it doesn't depend on theta. So it's just what? 0. Now that's very interesting. Look what it says. Let's erase this over here. d by dt of mr squared theta dot is equal to 0. This says something is conserved. Here's the conserved quantity right here. Angular momentum. Angular momentum, m r squared theta dot, its derivative is 0. That's the conservation of angular momentum. What did it follow from? It followed from, among other things, assuming that v did not depend on theta. If v had depended on theta, we would have gotten another term on the right-hand side here. So if v only depends on radial distance, then there's a conservation law. And this is very general. If you have a Lagrangian that doesn't depend on a coordinate for one reason or another, then there will always be a conservation law. We'll come back to that. That's going to be a very important theme, probably next time. Yeah, if you have a Lagrangian that doesn't depend explicitly on a coordinate, right, then there will be a conservation law, and it'll be a conservation of this quantity right here. Okay? We're going to come back to that. Incidentally, there's a name for coordinates which don't appear in the Lagrangian. It's a historical name. They're called cyclic coordinates, and there's nothing cyclic about them. Absolutely nothing cyclic about them. They're called cyclic coordinates if they don't appear directly in the Lagrangian. And theta is a cyclic coordinate. Now, of course, theta happens to be cyclic. It's an angle. But you can have all kinds of coordinates that aren't angles that can be cyclic. Okay. It's a bad name, but it is the name that goes with them. Whenever there's a cyclic coordinate, there is a conservation law. And the conservation law happens just because there's no right-hand side. There's a d by dt of something with no right-hand side, and so it's conserved. The thing which is conserved, partial of L with respect to velocity. Okay, but now that, just to go a little bit further, we can now say, look, I can't tell you what the angular momentum is. The angular momentum is determined by initial conditions. Whatever the initial condition was, it determines some angular momentum. Angular momentum is usually called L, but whatever it is, it doesn't change with time. So this tells us then, the angular momentum is equal to a constant L. It doesn't change with time. So once you know it, you know it. The initial condition tells you what it is, whatever it was to start with, it stays that way. And so what it tells you is that theta dot is equal to L over mr squared. That's what it tells you. We can plug it into here. We can plug it into here. I'll let you do that. Just plug into this equation here, theta dot equals this, and you get an equation just for r. You've figured out what theta is doing. The conservation law has told you what theta is doing, and now you can plug it back into the equation for r. Okay, the central points here, what are they? The central points are, number one, Lagrangians package problems in a simple and minimal kind of way. One function of all the coordinates and velocities completely determines all of the equations of motion. Number two, the Euler-Lagrange equations are a very, very efficient tool for changing coordinates. One way of saying it is that the Euler-Lagrange equations are invariant on the coordinate. They take the same form in every coordinate system. If it's minimum, and it doesn't matter what coordinates you use. So they're an efficient tool for changing coordinates. And number three, the idea of a conservation law coming when a certain coordinate doesn't appear in the Lagrangian. Okay, do we have any questions? There must be many. Or exhaustion.
Is there another motivation or meaning for the Lagrangian that captures some aspect of the system?
Is there another? Try a little more harder.
Well, is there an independent reason why you would arrive at the Lagrangian other than that it's the right thing to put in?
Oh, yes. It's called quantum mechanics. But for us now, it's simply a fact of experience. Not a fact of experience of pushing things around and so forth. I'm talking about the experience of basically 100 years of classical physics in the 19th century between the end of the 17th century and the later part of the mid-19th century, that many laws of physics, it was realized, could be cast in this form. Not just particles moving around, incidentally. Waves, electromagnetic fields, everything you can think of is cast in this form. So, as I said, a matter of experience, meaning the experience of physicists for 100 years or more than 100 years, eventually led to this framework. And there are no examples, there are no known examples of laws of physics that don't fall into this framework. If this was all there was to it, we would be puzzled. Why is this true? The answer is that it's a deep aspect of quantum mechanics that leads to it, but that's for a later time. Okay, yeah.
In the lagrangian you have on the right-hand side of the board, can you resolve the energy there into kinetic energy plus a potential energy? Because it looks like that last term is neither kinetic nor...
That's right. Okay, we need a deeper concept of energy. The deeper concept of energy is called the Hamiltonian, and we will come to it. This is the Lagrangian form of the equations, but I will tell you anyway what the energy is. The energy is just the sum of these two. This does not contribute to the energy. Exercise. Prove that the sum of these two is conserved. Take the equations of motion and prove that, that the sum of these two is conserved with time. I don't want to do it now because we're going to do it in a uniform way when we study the Hamiltonian formulation of classical mechanics. But it's a good question. What happened to energy? Answer, this one doesn't contribute to energy at all. All right?
Question. If you know you're describing a object curving through a trajectory.
Curving? Yeah.
Yeah, with Lagrangian, what if that curvature is caused by a gravitational field?
Well, first of all, we're not thinking about general relativity.
True.
Right. If we want to do, all right, gravity is all set up for us here. All we have to do is remember what V is for a gravitational field. What is a gravitational field of a massive object? M, little m, the mass of the object, times big M, the mass of the gravitating center, times G over R.
But not for general relativity.
No, but we're not doing general relativity at the moment. General relativity is a long way down the line.
So, excuse me, those energy terms,
Yeah.
You stated earlier they're from fictitious forces. So are no, that's the kinetic. So are those fictitious energies?
Look, fictitious is a funny word.
Well, no, because we're talking about you're on the merry-go-round and you're seeing something,
Yeah.
and by definition in the first coordinate system you said no forces.
Right.
Okay, but from a merry-go-round it looks like there are forces.
Right.
So then you would back calculate and it would look like there were energies.
Right.
So they're
The person
fictitious.
in the rotating frame of reference will say in every possible respect, this is a potential energy, and that's a, so the answer, okay, so what's the answer? The answer is that energy is not something which is invariant under coordinate transformations in general. In particular, it's not invariant under time-dependent coordinate transformations. Given a coordinate, given this problem, there is a conserved energy, but it is not the same energy that that the other fellow in the rest frame said. Actually, it is. I take that back. It is the same energy, isn't it? Remember where this came from? Let's see. Where did it come from? No, it's not the same energy. Yes. No. No, not quite. No, it's not.
It has no energy in the rest frame, but when you're in this rotating frame.
Yeah. That's right. It could be, you could, that's right. You could have a particle at rest in the, let's see, what do we want to do? A particle at rest in the rotating frame. Now, it won't stay at rest in the rotating frame, but somebody could be holding it. If they were holding it, it would have no kinetic energy. Well, no.
The particle's at rest in the stationary frame. How does it look from the rotating frame?
Oh, it moves around in a circle.
Right. So
It moves around in a
looks like
circle.
it has kinetic energy.
It looks like it has kinetic energy, right. Right, but it also has some centrifugal energy. Right, has some centrifugal energy also.
Well, that's
true. But that term gives it no energy. There's no energy there. Yeah, so energy is another subject. Energy is not a terribly natural object in the Lagrangian formulation. It's a very natural object in the Hamiltonian formulation. We will come to it. Anything else?
A question? In where you have that, the rightmost term, x dot, the perpendicular term, if I can call it that,
Yeah.
up in your, on the left.
You know, here, right.
Sure. Up, on the red coordinates up there, I was wondering if, I was trying to draw, using the red x-axis, that component from
Yeah.
this point of view.
Okay,
I don't
so-
know how to draw that.
Right, so let's draw the red axis as being stationary, as if we were in the red coordinate frame. And you want to know,
What that final, what
Yeah.
that final force or perpendicular component.
well, let's
It's
look
going
at
to be proportional to y dot.
All right, whatever it is, this is, all right, where is it? Where is the force? The force is, what was the x component of force? Well, it was proportional to y dot. There was some coefficient. And the x component and the y component of force was proportional to minus x dot. Yeah, there's an omega there, probably an m, but the important thing was the y dot and the x dot. All right, so the first thing is that this force is perpendicular to the velocity. How do I see that it's perpendicular to the velocity? I take the dot product of the force with the velocity. That'll be f of x times x dot plus f of y times y dot, x dot, y dot, and they cancel. So first of all, if the particle is moving in some trajectory, the Coriolis force is always perpendicular to it. Whatever the direction of motion, the Coriolis force is perpendicular to it. It's proportional to the magnitude of the velocity. That tells you a lot. There's not that much more to know. It's proportional to the magnitude of the velocity. Let's go back, take this away. So it's perpendicular to the velocity, proportional to the magnitude of the velocity, and proportional to the angular momentum, the angular velocity of the coordinate system.
Thank you.
So all this discussion about energy, one thing, when you compute the Lagrangian, you're doing it in an inertial frame, right?
Well,
I mean, you won't,
You would start out computing it in a rotating.
yeah, you probably wouldn't start out in a rotating frame, right? You probably wouldn't. But I think the lesson here is that not so much that you start with a form of the equations of motion that you got from somewheres. You got from somewheres, and here is how to transform it from one coordinate system to another, right? But yeah, sure. Typically, for a problem involving particles like this, you might say, look, we know the answer in the inertial frame.
but I mean, you wouldn't write down the Lagrangian as, I mean, this seems obvious, but as m over 2 big x dot squared plus y dot squared, just a priori, because kinetic energy is in an inertial frame of reference, right?
Right.
Yeah.
Right. No, the rule is, Newton's rule is that in an inertial frame, the laws of motion are Newton's equations, which translates into the statement that in an inertial frame, this is the form of the Lagrangian. Right. Incidentally, this kind of term here is not particularly unique to Coriolis force. You know any place else where a similar term like that occurs? Charged particle in a magnetic field. Right. For a charged particle in a magnetic field, you would have the charge of the particle and the magnitude of the magnetic field. In particular, if you had a magnetic field pointing into the blackboard, or out of the blackboard, either way, charged particle of charge E, magnetic field B, uniform magnetic field, this would be the form of the Lagrangian.
Are there any constraints on what kind of function can be a Lagrangian other than smoothness?
There are, and we'll come to that. But at the moment, I haven't told you anything that would make you suggest there are certain kinds of constraints. But the answer is yes. And incidentally, one thing, an exercise is to take those equations of motion. I lost them. Where are they? They're of the form x double dot is equal to omega, what is it, omega squared x plus y dot, I'm leaving out masses, y double dot is equal to omega here, omega squared y minus omega x dot, something like that. Can you prove that one of the trajectories of the system is just moving in a circle about the origin? It better be, because that's just the original particle standing still somewhere. Moving in a circle would be what the person on the carousel sees. So you should be able to see that gives rise to a particle that moves on a circle. Once you know that, then you should know that particles in a magnetic field move in circles. These equations are exactly the same.
Would remain in the same circle or would tend to go out?
No, it remains in the same circle. Yeah. There are solutions of the equations where it just stays in a circle. Of course, you can also have it moving out. Without this term, it wouldn't move out. This term, which is important.
A divergence, though. A charged particle moving in a circle. I remember
In a magnetic field.
Let's say not in a magnetic. Let's just say some force is making it move in a circle.
Okay.
And I remember a long, long time ago, something about physics says that that's unstable. It's going to radiate energy and collapse.
It'll spiral into the origin.
Okay.
And so will it here. These are the equations without taking into account radiation. Radiation is another story.
Okay.
No other questions?
Where do we get hurricanes?
Where do we get hurricanes?
They're fictitious.
Yeah. Coriolis course, I'm told, is very important to them. Are there any meteorologists here? Can you explain?
No, I can't. So this framework is thought to cover everything,
Yeah.
correct?
Everything classical.
But an analogous framework would be thought to cover everything else as well.
Everything that we know about, yes.
So if somebody came across some principle of physics that you were not able to cast into this Lagrangian formulation, that would be like a revolutionary
Absolutely.
thing.
Right.
Because it comes from quantum physics and that can't,
Now, there are phenomena which look like they come from equations which are different than this. For example, just the phenomena of a particle moving through a viscous fluid. But the reason why these equations don't look like the right equations is because you're ignoring the degrees of freedom of all the molecules and everything else. As far as we know, and we certainly know about molecules and atoms and all that sort of stuff, everything in nature, when everything is taken into account, falls into this pattern. General relativity, Maxwell's electrodynamics, the standard model of particle physics. And, you know, these days when a particle physicist is, or a particle, any kind of physicist is interested in trying out new laws of physics, trying out new equations and so forth, the usual pattern is to write down a Lagrangian, and then from that derive the equations. Now that's not to say someday somebody may not discover something else. It looks unlikely, but at the moment, the action principle is extremely general.
For more, please visit us at stanford.edu.